So we're going to enter this information into the calculator and do a 2-sample T test for a gas mileage of US cars and Japanese cars from this data. So here's the number of cars. Here's the mean mileage. I guess that's US cars. Here's the standard deviation. Here's the standard error of the mean. So what that is S over root n. So this divided by root n. It's the estimated standard deviation of this number. So if that's approximately normally distributed, then you go the 2 standard deviation away from that would be approximately where you expect to find the actual true mean based on the data. So plus or minus about 0.8 would be maybe the right answer. We're not worried about that now. Here's the other sample. It's 79 cars. The mean is 30.48, standard deviation 6. Similar standard deviation, but a lot larger mean, a lot smaller sample size. Here's the standard error. So if I was looking at that without knowing any statistics, and I look at there's 249 cars, the average gas mileage is 20. And for 79, the average gas mileage was 30. It's clear the second group of cars has higher mileage, but fine, we'll just go ahead and see what a 2-sample T test says to see if the second group has a bigger mean. So here's the null hypothesis, that the two means are equal. Here's the alternative. Mean of 1 is less than mean of 2 long-term. So that's just the sample mean. The population mean is what these things refer to. So we've sampled all the cars. What would the mean be for the two groups? Could they be equal, or is the first one pretty well guaranteed to be less than the second one? So we come in here. We just go stat tests. We go to the 2-sample T test. There it is. Boom. We tell it we're going to use data. Okay. I'm hitting enter. No, we're using stats. Pardon me, that's why it doesn't change. I'm hitting enter. Okay, and then we come down here. We'll clear this. So the mean was 20.14458. We don't need all those decimal places, but what the heck. And the standard deviation, hit clear, 6.41470. Looking as I go to make sure I don't screw up. And then the N, clear that, 249 observations. The second mean, 30.48101. Enter. Standard deviation, 6.10771. Enter. Sample size, clear that, 79. Let's make sure I have some confidence in what I typed. It's easy to screw up. N2 is 79. X bar 2 is 30.48. 6 looks okay. The alternative we're looking for is mu1 is less than mu2. Okay. And here's that pooled. We go no. There's the color. I don't care. Here comes calculate. Well, let's see what happens. So what are we expecting? I think that mu1 is less than mu2. When I compute the T statistic, I get X bar 1 minus X bar 2. It's going to be a big negative number, and I'm going to be dividing by something that doesn't make it get smaller. So I expect to get a large negative answer for T. And since that's a left tail test that we're looking at there, the tail probability will be small, corresponding to that negative T value. And so we'll get a small P value. Here we go. T is minus 12. So that's what we were saying, that in terms of what's going on here, under the null hypothesis, you expect the values to follow a bell curve like this. And back here is maybe minus 3. So we got here a T of almost minus 13. And then for the P value, we're going to get this tail area. This is basically going to be 0. Okay. And it's got the degrees of freedom there. It's 136. And change, 0.87. The easy degrees of freedom that you might use if you just doing this by yourself is the smaller of one less for each of these. So that would, the smaller of the two. So that'd be 78. It's not going to matter too much because we're going to be looking here. If we use the tables to do our job, here are the tables. And we're looking at 78 and 136. So when you use the tables and you can't find your number, like 78 is not there, we use the next smaller number. So we're going to use 70. So we don't go bigger, we go smaller. And for 136, we're going to use 100. Okay, since the number of observations is so high, we could probably be better off using the formula degrees of freedom if you had access to it. But if you don't, you should be fine using the smaller of n1 minus 1 and n2 minus 1. So now we have our second problem. We got minus 12. So here on the t tables, it only lists positive values. So we would take the upper tail probability corresponding to 12, and that will give us the tail probability on the left for minus 12, since that is symmetric. So now we're looking for 12. Bad at my pen. Okay, look for 12.94. Here's the tables. Where are we? Say 70. Get in here. Struggle. There's 70. I'm looking for 12. You're not going to find it. You see this? These keep getting bigger. You'd have to go over here a couple miles to get to 12. And the same thing with 100. And so the tail probability, the smallest one they have is 3 zeros and a 5. The actual p-value would be formed by taking a t way out here, a lot smaller than 3 zeros and a 5. So we'll just say the p-value is less than 0.0005 in both cases. P-value, we can't find our number. We'd have to go further to the right in the distribution. That would further shrink the tail probability beyond that tiny number that exists for a t of something like 3 or 4 to get all the way up to 12, which is going to shrink it a lot. So we can say it's probably a lot less than 0.005. And we know it is because here in calculator land, it said 0. Right. So it's beyond the ability, I think, of the calculator to display. It's more like 10 to the minus some giant number. And when that happens, they just give you 0. Let's see what we got here. So that is how you enter that into the calculator. Let's see how we did. So here's some things we might try. The t value we're reading off the calculator is minus 12.94. We know how to compute that. It's x1 bar minus x2 bar over square root s1 squared over n1 plus s2 squared over n2, if we wanted to compute it. Assumption checking. Well, we've got a large sample. So really, I just need SRS, simple random sampling. So that would say that we pick cars at random of American cars, and we pick cars at random for Japanese cars. If we weren't picking them at random, we might have picked cars that had higher mileage and lower mileage because we're not picking them randomly. So as long as that's happening, and that doesn't say that here, it says a sample, but you have to look into that. How do they sample? How did they do it? You'd have to know that to make sure the sample is representative of the population you're trying to study. State the results. We would say reject HO. Mu1 appears less than U2, conclusive or strong evidence that the Japanese cars have higher average mileage, miles per gallon, I guess we call mileage miles per gallon, like that. Now, if you wanted to get a little more serious about it, it says, ordinarily when you do that, when you reject the null hypothesis, you might want to compute a confidence interval to see just how big it is. So having rejected the null hypothesis, claiming there's a difference, well, how big do you think that difference is? The hypothesis test just says there's a difference. The confidence interval says how big it is. So let's go do that. I think I could just get by here and go back to stat, wrong place, stat, test. Now I'm looking for a 2 sample t interval, 2 sample t, yep, okay. And luckily it remembers everything I stuck in. Got the confidence level of 95, I got the right sample size. Those are the numbers, right? Yep, down we go. And we got pool turned off. Pool that can also be done with the confidence intervals, but we did not demonstrate what that looks like. We don't want to use it anyway. Oh my. So it says the difference in mileage is somewhere between 11.92 and 8.75. So if that is something you care about, that's how big the difference is. It's minus 11.92 up to minus 8. My mouse is over there. Okay, 0.758, like that. So what that says is the true average the true average difference. I'm having trouble today. Here we go. True average difference is between minus 11.92 and minus 8.758 mpg. Most likely. So we do have, it is a confidence interval, so it's not guaranteed to capture the true difference. But it has a 95% chance of capturing the true difference. So we just say that's most likely correct, that on average, Japanese cars are between something like 12 and 9 miles per gallon more fuel efficient than American cars. Okay, so that in theory could be the last of the regular lecture videos I'm making. And the road has come to a close, except I'll be making videos throughout the semester, which you will have seen already once you get to this point. I'm thinking I'm going to stop sharing now. Oh no, I'm going to stop recording. How about that? Stop recording.